Welcome everybody to the 9th lecture of Digital Communication course. In today's lecture we will talk about a new topic called intersymbol interference. Basically, intersymbol interference is one of the impairments that's caused by the channel or the filters at the transmitter and receiver. And we need to understand what's this intersymbol interference, how does it affect our system, and how much it will degrade the bit error rate, and how can we handle it? What's the criteria to avoid intersymbol interference? So in the previous lecture we studied additive white Gaussian noise and how is it related to the bit error rate performance of your system, and why do we need to use the matched filter in order to increase the signal to noise ratio. Here this is another type of detrimental caused by the channel filter or the transmitter filter. So we need to understand it and handle it, both mathematically and practically. So this is basically intersymbol interference causes bit error rate degradation, beside the degradation that caused by the additive white Gaussian noise channel. If you remember with me in the first lecture, we explained the block diagram of a digital communication system. And mainly, some of the blocks, they were shaded, and some of them, they were not highlighted or shaded. And I told you the difference between these blocks and those blocks is the fact that these blocks are fundamental to your system. You must use them in order to be able to communicate and build your communication system. Whereas there are blocks that are redundant, but when you use them, you get extra merits and advantages. So let us together remember the basic digital communication system we have right now. Usually we have input binary data. We denote it by PK. Then this passes to pulse amplitude modulator, and this maps, for example, 0 to plus A, 0 to 1 to plus A, 0 to minus A. And then we have transmit filter, which we call it G of T, denoted by G of T, and this is very important actually. And then we have what? We have channel, which can be baseband channel, wireless channel, line channel, microwave channel, transmission line, whatever. You have a channel. This is at the point where you transmit your data out of the receiver. And then when the signal reaches the receiver, there is an additive white Gaussian noise that gets added to your received signal. After that, you have receive filter as well to manipulate and adjust your received symbol in such a way that you get rid of the impairments of the channel as much as you can. And then you have sampling and then decision device. The receive filter here also includes the max filter. So both of them, we call them in general receive filter. So you have here the transmitter side, you have here the channel side, which is H of T and W of T, and you have the receiver side. As the input binary data travels from the transmitter to the receiver, it passes through 3 filters. We call this the transmitter filter the first type filter, the channel is the second filter, and the receive filter is the third filter. So what's the total response of this system? The total response of this system is C of T, which is G of T convolved with H of T convolved with C of T. This is the total response of the system. Because you have 3 filters, the response of each filter is given. If I tell you find the response of the whole system, you just convolve all the filters with each other. If you find the convolution hard to be found in time domain, you just go to the frequency domain, take the Fourier transform of each filter, you go to the frequency domain. So if you have convolution in time domain, what will you have in frequency domain? You will have easy multiplication, which becomes much easier for you. People usually tend to use multiplication rather than convolution, because convolution has integration and shifting and this. So a way to solve this problem is to go to the frequency domain and do multiplication there, so that you get what? The response in frequency domain. To get the response in time domain, the response of the whole system in time domain, you just take the inverse Fourier transform and you go back to the time domain. So this is understood, very well understood. We just reminded you of the basic communication system, digital communication system. So what we need to do, we need to find the total response of the system. The total response of the system is given in terms of P of t. This is function, we call it P of t, and this includes the response of the filter at the transmitter and receiver and the channel between them. So what's P of t is equal to G of t convolved by H of t convolved by C of t. And I just mentioned how to find it in the frequency domain if you are not able to find it in time domain. Now, the way you transmit your data sequentially, back to back, in successive manner. Yes? So you have your data symbols, which are AK. AK are basically plus A or minus A, which are corresponding to 0 or 1. Yes, your data bits 0 or 1. After you do pulse mapping, 1 becomes plus A, 0 becomes minus A. And you have, for each data, you carry it over a pulse, over transmit filter shape. So this we denote it by P of t minus KTB. Minus KTB, K can be any number from minus infinity to infinity. As you can see here, K is not defined, can be any number basically. And this TB means each TB duration you are transmitting one data bit. Plus N of t is the noise. In the previous lecture we denoted W of t as noise. Here we use N of t. So we assume that the system impulse response is normalized by setting P of 0 to 1. This is how you normalize it. So the overall system impulse response frequency domain can be found by taking the Fourier transform, as I just mentioned. In this case, instead of P of t, you have P of f, and which is equal to GF, which is the Fourier transform of small g of t, multiplied by H of f, which is the Fourier transform of small h of t, and C of f, which is the Fourier transform of small g of t. This, I'm talking about this C of t, the receive filter in time domain, this h of t, this g of t. So when I go to the frequency domain, they become like this. So instead of having convolution as given here, you have multiplication, which is much easier to find. Now, the receive filter output y of t, after the receive filter, you need to find what's the system model of your signal in terms of equation and formulas. So the receive filter output is sampled at time equal ITB. Each TB, you take a sample, and we usually prefer to take that sample at the peak of the pulse, point where it doesn't have interference with all the other previous pulses or coming pulses. So y of t at time t equal I is equal to mu. Mu, this is constant for scaling purposes. Summation from k minus infinity to infinity, assuming your transmission took long period of time, of AK are the data symbols, multiplied by the pulse, P of I minus K TB, and of course plus noise, because noise is always there. So you need to consider it in your system model. So what's this? If you simplify this expression a little bit more, you can take the case where I is equal to K, which is equal at the 0, and therefore you have a new term here, which is UAI, which at the point where I is equal to K, plus U summation K from minus infinity to infinity, but with K not equal to I. All the time instances where K is not equal to I. AK P Ti minus K TB plus N of T. So this is your received filter output. The term UAI represents the contribution of the ith transmitted bit. We call it the desired bit. This is the bit that we are interested in decoding. The term U multiplied by the summation of AKPI minus KTB represents the residual effect of all other transmitted bits, and this is, we call it the inter-symbol interference. These are the pulses that are interfering with your desired signal, and you want to get rid of these pulses. You want to make sure that although they exist there beside your desired pulse, you don't want to receive any interference from them, so that you get your data with high reliability. Because if any mismatch, any misalignment, you get too much interference, and the interference becomes like noise, degrades your system performance, and your bit error rate, instead of being 10 to minus 6, which is good, becomes 10 to minus 3, which is really bad. So your video streaming will stop working. You will not be able to decode your video, because video requires high quality, for example. In the absence of both ISI and noise, ISI, then it's inter-symbol interference. In the absence of both ISI and noise, the sampled output will be only YTI equal mu AI, just the data you are interested in decoding. So no interference from all the other previous pulses. When the signal to noise ratio is really high, which is the case in telephony systems, ADSL and Turk Telecom kind of companies, the operation of the system is largely limited by ISI. What it means that the performance of the system heavily dependent on ISI only in these cases, because you transmit your signal with high power in telephony systems, and in this case the noise will be ignorant, because it will be so small that it doesn't affect your performance. What affects your performance is the inter-symbol interference. So, to summarize things for you and make it easy for you to understand, noise can be defeated by increasing the transmitted power. Increase the transmit power, you reduce the noise. Yeah, you don't reduce the noise, but you go far away from the noise level. In this case, you can decode your data successfully. Inter-symbol interference is a problem, happens and appears usually because you want to transmit your data as fast as possible. When you want to transmit your data as fast as possible, the symbols interfere with each other. Their pulses interfere with each other. To avoid inter-symbol interference, you must not exceed certain data rate, or you must design intelligent system with special pulses that can avoid such cases. This is really very critical thing, actually. So Nyquist criteria for distortionless. So we said we want to understand when we can transmit our data successfully while avoiding inter-symbol interference. There is a criteria that we need to comply with it, which is called Nyquist criteria. In order to eliminate the inter-symbol interference completely, we need the residual effects, the term that I just showed you, the residual effects from all symbols on the ith symbol, the symbol you want to decode, to be zero at the sampling instant. Yeah, it means all the contributions coming from the adjacent pulses to your pulse will be zero. Also, we need the output of the sampler to be YTI equal UAI, exactly, without any interference. This means that the term BI minus K TB equal to 1, perfect one, when I is equal to K, which is the point at which I want to decode, or 0 when I not equal to K. If we take the Fourier transform of the previous equation, then we have, instead of being in time, becomes in frequency. So you get this equation, RB is the data rate, which is equal to 1 over TB. Everybody remembers that. This will help you. RB is equal to 1 over TB, and this is in the frequency domain. We call it transfer function now. We don't call it impulse. We don't call it system response. We call it a transfer function of the system. The Fourier transform P delta of f of an infinite periodic sequence of delta functions of period TB whose individual areas are weighted by the respective sample values of PT is given by the following equation. This is the Fourier transform of P delta of T. So it's basically equal to the, what's the Fourier transform? Integration of the function you want to transform multiplied by e to minus j2 by ft. This is the Fourier transform. So this is basically the successive delta functions weighted with the amplitude of the pulse you are transmitting, and when m equal I, in this case m is equal to I minus k, and in the case when I is equal to k, in this case m equals 0, and if you substitute here 0, what happens? You have p of 0 delta t e to minus j2 by. What's the integration of this function? It's simply this, that this becomes p of 0, which is equal to 1. If you just integrate this, e to minus j2 by ft, again e to minus j2 by ft over minus j2 by f, and the integration from minus infinity to infinity, substitute the value, you will left with just p of 0. P of 0 is equal to 1 because we already at the beginning we normalized it and we made it to be 1. When I not equal to k, this means that m is not equal to 0. In this case, p of 0 is exactly equal to 0. What does this mean? This means that when I am not at the point where I want to decode my desired signal, I get 0 contributions from all the other adjacent symbols or adjacent pulses. Where I get one unity when I am, here I get one unity when I am exactly at the point where I am interested in decoding my signal. So in this case, you just do the same thing, similar to the previous equation, and you get the value to be 0. Now, the system transfer function P of f can be derived from the equation presented in slide 9, which is this. This is the equation. And P delta of F is equal to RB summation PF minus NRB, which is equal to 0. Therefore, summation of PF minus NRB equal to TB, or 1 over RB. The Nyquist, what's the ideal Nyquist criteria? The Nyquist criterion for distortionless baseband transmission in the absence of additive white Gaussian noise states that the frequency function P of F of the channel eliminates intersymbol interference for samples taken at intervals TB, provided that it satisfies this condition. So you take your sample at intervals equal to TB so that you ensure you don't have intersymbol interference because of the adjacent pulses. Now, how can we satisfy this rule? To satisfy this rule, the frequency function must be in the form of rectangular function. That function satisfies the previous rule that says we can avoid intersymbol interference if we ensure we have this formula. Now, why rectangular function can satisfy this? First, let's see rectangular function in terms of its mathematical formula and its graphical representation. P of F in this case is equal to 1 over TW, where F, the frequency, is bounded between minus W and W, and it's 0 otherwise. When F is greater than W or F less than minus W, it's 0. This, if I ask you to draw this, you will exactly get this pulse. So P of F is basically 1 over 2W multiplied by rect F over 2W. 2W here represents the width of the pulse. 1 over 2W represents the amplitude. So this is in the frequency domain. What will you get in time domain? You will get sync. Because how do you go to the time domain? Inverse Fourier transform of this. You get sync with proper parameters, with the proper values at the x and y axis. So the overall system bandwidth W appears in P of F equation, which is defined as follows. W, the bandwidth here, is equal to RB over 2, which is equal, since RB is 1 over TB, it becomes equal to 1 over 2 TB. The special value of the bit rate, RB, is equal to 2W, is called the Nyquist rate, and W is called the Nyquist bandwidth. So at each RB, which is equal to 2 multiplied by W, you take sample at the peak of the pulse, so that you avoid getting intersymbol interference from the adjacent pulses. This is the criterion. If you follow this one, you will not get any intersymbol interference unless your channel H of T introduces this. So this is the sync I was talking about that you get when you go to the time domain. So if you have this in the frequency domain, you get this in time domain. As you can see in time domain, these are the sampling instances at RB equal to 2W, TB, 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 the duration between them. And you have peak of 1 here and width of 2 TB. 2TB 1 over 2TB half RB. RB is equal to 2 multiplied by W. Yes, from here to here, the width of the pulse, which can be obtained by taking the inverse Fourier transform as I just mentioned. Now, if digital binary bits are passed through a pulse shape filter, which is the transmit filter, we call it sometimes pulse shape filter, all the bits take u p of t minus ITB. All the bits with pulses, this is the p of t is the pulse shaping filter, which is equal, since we are in time domain and we want to transmit our data while considering that there is no intersymbol interference, then we must use sync. Sync 2 by W. In this case, the received samples at t equal ITB are intersymbol interference free. Let's see, let's visualize this together. You have the first pulse, you have this sequence, the binary sequence. 1, 0, 1, 1, 0, 1, 0, and you want to transfer it to send it over the channel while avoiding intersymbol interference. You try, 1 corresponds to plus A. Plus A, you multiply it then by P of T, which is sync. So it becomes sync. Let's say A was 1, and you multiply 1 with sync, then the answer becomes sync. Sync, you draw sync here. Then 0 comes, 0 corresponds to minus A, means minus 1. Multiplied by sync becomes up, from down to up, the pulse. And you have 1, up, up, down, up, down. Now, where is the catch here? Where is the trick? Now see at this point where you need to sample at the receiver. At the peak, you get the maximum power of your desired signal. At the peak, yes, here at the top, you have maximum power, maximum energy. Now, at the top exactly, this value is perfectly 0. Means all the signals here coming at this point and their values exactly 0. Means there is no intersymbol interference. This means that this whole term that I was talking about, this term, this is the crossing point. This is where intersymbol interference is 0, made to be 0. And at the peak, I get this, UAI. And this, the summation of all the signals, you sum it normally. I sum it. Because when you sample, you take whatever you see at this instant of time. But as you can see, when you use sync, at that point, all of the pulses sum to 0, which is amazing. You avoid intersymbol interference. This is how we link math to visualization. And then again, test another pulse. Let's take this, the third one here. At this point, which is corresponding to the peak, you have zeros. You have 0 crossing here. Means you have no intersymbol interference. And so on and so forth. Which is, this is how you can avoid intersymbol interference. By transmitting your data at Nyquist rate, RB is equal to 2W, where W is the bandwidth of your pulse in baseband, not in passband, or W is equal to 1 over 2 TB. However, although this is what we expect to find, if we use rectangular pulses in frequency domain and sync pulses in time domain, this is really difficult to achieve in practice. This is what theory tells us, and we applied it. Seems fantastic. We loved it. There is no intersymbol interference. But when you come to practice, you find that there are severe problems. What's the first problem or first difficulty? with such a pulse. It requires an ideal, this Nyquist pulse, which is sync or rect. It requires an ideal low-pass filter characteristics in frequency domain, which is physically impossible. Now, if you remember in the previous semester when we talked about the rect, and I said rect is composed of infinity number of harmonics. And to make rect, you need to take so many terms, and you can never get the exact precise rect. You get always ripples at the edges. Ripples go like this. The more terms you get, the more terms you take, the less ripples you will get. But till when? So this is one of the key practical problems with rect. You cannot practically design it, get it. In math, it's easy. Just put the function, you get the curve, you get the pulse that you want to use. But in practice, you need to use filters to generate such a pulse. And when you use filters, you need massive amount of terms, fundamental terms, and you cannot really let your filter take all these terms. The second difficulty that we have, the function p of t decreases as 1 over absolute value of t. What does this mean? This means that, see here the tails, here. We call this the main loop, the highest one. Where these ones, we call them tails, the tails of the sync. As you can see, they have still large values. Instead of using the power of the pulse only in the region where my data is located, I'm using it in other regions where I'm not benefiting from it. And it causes interference to other adjacent pulses if I put beside it. So why don't I reduce this a little bit? This is fundamentally a problem in communication system. We want to use pulses that are localized in time and the frequency. But what happens to the pulse? If you localize it in time, it pops up in frequency. If you localize it in frequency, it pops up in time. So you cannot, by theory, by math, by physics, you cannot localize a pulse, means squeeze it in both time and the frequency simultaneously. It's a trade-off process. So you fix it in one domain, you get hurt in the other domain. And this is fundamentally a problem. We need to find what's the best trade-off according to our application, to our use case, to our scenario. And based on that, decide where do you want the pulse to be localized more? Is it in time or is it in frequency? And at the expense of what? If you localize it in time, what happens? Spreads in frequency. Frequency is bandwidth. Bandwidth is money. Money is cost to the company. If you squeeze it in bandwidth, it will spread in time. If it spreads in time, causes interference to your adjacent symbols and your data, you will get errors. And your system will not be considered working successfully. And if it doesn't pass the test, the company will not buy it, and accordingly you will decrease your sales. So you are getting hurt from both sides. So you need, as an engineer, you need to understand the use case, the scenario, and design an optimal solution for that so that you can minimize the cost in any of the domains, time or frequency. So what do? If we find the problems, and as engineers, we need to find a solution for it. Problems are opportunities for us, because if we don't have problems as engineers, then we don't have work, we don't have jobs. So problems are opportunities for us, triggers us to think, and when we come up with solution, these solutions solves our problem, and then after that we reward you, we give you salary, We give you some awards, some recognition that you solved this problem. So now apply it to here. How do we deal with these difficulties? The first obvious thinking is to design a pulse, a different pulse, that can somehow be flexible between the time and bandwidth. Reduce the ripples so that you reduce the interference and allow some bandwidth expansion. Don't squeeze it too much in frequency. So you have now trade-off. If your design wants low bandwidth, you squeeze more in bandwidth and you allow some ripples. If there is plenty of bandwidth, the company is very rich like Turkcell, and they have bandwidth, too much bandwidth, they tell you don't worry about the bandwidth. The most important thing, you make the bit error rate 0 if you can. I want my phone call to be received at any place, wherever I am. No errors, no degradation, no drop calls. So here, that's why always when you need more quality, you need to be willing to pay some resources in terms of bandwidth or time. If there is a small timing error, now this is just to make you understand these problems more. This is the first problem and the second problem. Now here a case, practical case. If you have a timing error, what's timing error? Instead of starting your synchronizer at time equal, suppose t0, you started it after t0 plus 0.0 second. This causes some mismatch. We call this jitter error. Between the transmitter and receiver, they are not exactly synchronized. This will result in a significant inter-symbol interference. Why this is significant inter-symbol interference? Anybody can tell me? Suppose these are not exactly coming perfectly because of lack of synchronization between the transmitter and receiver. Any small shift, what will happen? If you have any small shift, you will get inter-symbol interference because you get only 0 inter-symbol interference when they are perfectly aligned at this time of point. At this instant of time, you get 0 interference. If any shift to left or right, you get inter-symbol interference. And it becomes disastrous. Imagine you shift by like half TB, you cannot recognize your data, you cannot get it back. So this is really critical. So the point that I want to make here is we need to have some pulses which are a little bit tolerant to this error. I mean, damage and destroy my system just because of 0.001 millisecond. A little bit allow some synchronization errors because synchronization is a difficult problem to achieve in practice. This is one problem. The other one, the more practical solution. Now this is the problem, and the other problem I told you about is the interference. The high ripples also not forces you to put your pulse away from the first pulse so that you reduce the interference. If they are not exactly, if you are using pulses with different shape, and you want to put a pulse with adjacent to sync pulse. To reduce the interference between them, you need to go far away. If you go far away, you reduce your data rate because it's in time. If you reduce your data rate, you don't send high-speed internet. So you want pulses that are, we call them friendly pulses, can coexist with any other pulses without being far from these pulses, so that you can transmit. And the same frequency, if you go far in frequency, you waste bandwidth. Bandwidth is money. The more practical solution to address the previous problems is to design the channel transfer function P of f based on the raised cosine spectrum. Here we have a new term, a new technical term. We call it raised cosine. This raised cosine is a pulse like rect pulse, but has different shape. Different shape to solve our problem. Let's study this pulse and see its characteristics and understand how it can help mitigate these problems. The pulse, the mathematical formula of this pulse is as follows. If from 0 I define a new frequency between 0 and W, here, let's start from here. You have this rect, yes? Between 0 and W, here, between 0 and W, I define a frequency F1. At this F1, before F1, I use normal rect. After F1, I use another function that decays fast, not sharp, with a slope, decays with a slope. Let's see. So this is the function that decays with a slope. And this is rect, normal rect. Before frequency equal F1, it's normal rect. But after F1 till W, it's with slope. The curve becomes with, and after that, 0. Let's see the shape of this in practice. This is the shape of the pulse. So as you can see, let's say this pulse, the middle one here. Everybody with me, this is the middle one here. At t equal half, at frequency equal half here, f over w equal 1 over 2. Before 1 over 2, you have rect. After 1 over 2, you have function with slope. And after this, you have 0. This slope, you get it from where? From this formula. If you draw it in MATLAB, you will get that function. The frequency parameter F1 and the bandwidth W are related by the following formula. We define a new variable, we call it alpha. Alpha is equal to 1 minus F1 over W. The parameter alpha is called the roll-off factor. I will ask about this in the exam, and many people you will find in the papers talking about this. Roll-off factor. When you hear roll-off factor, then it's alpha. And this determines the slope of the curve, the bandwidth of the raised cosine pulse, and its slope. The roll-off factor indicates the excess bandwidth over the ideal Nyquist bandwidth W, which is coming from the rect. The transmission bandwidth BT is defined by BT equal to W multiplied by 1 plus alpha. So this is the new transmission bandwidth. In the previous case, when I had rect, what was the transmission bandwidth? Exactly W. Here, since you use a pulse with larger bandwidth a little bit, actually you can control its bandwidth by alpha. Alpha can take value from 0 to 1. The new system bandwidth becomes W multiplied by 1 plus alpha. If alpha is equal to 0, what do you get? The rect. You return back to the original case, the ideal Nyquist pulse. Then the transmission bandwidth is W, which is the Nyquist bandwidth. This is the minimal bandwidth you can use to transmit your symbols without inter-symbol interference. However, if alpha is equal to 1, substitute here 1, you get the transmission bandwidth equal to 2W, which is equal to twice the Nyquist bandwidth. If alpha greater than 0, then transmission has to be at a lower bit rate to avoid inter-symbol interference. Now see why. If alpha greater than 0, this is alpha half. Greater than 0, this is alpha 1. What happens to the bandwidth? Increases. Now the bandwidth increases. What happens to the sync? Decreases, shrinks. And to avoid inter-symbol interference, you need to transmit at a lower bit rate. This is the disadvantage of this solution. So the impulse time response P of t is obtained by taking the inverse Fourier transform of the frequency response. So this is P of f, this is in frequency, this is the shape of your new design pulse, the raised cosine. And when you go to the time domain, you get this function, which is basically sinc, the previous sinc we know, multiplied by another function. This function is basically used to decrease the tails of your sinc function. So instead of having tail of this size, you get tail of this size. When you multiply your sinc with cosine, you get new function with reduced size, with reduced tails. The P of t function is plotted graphically in the following slide. See the function here? Now I will ask questions like this. What will happen to the sinc function in time domain when you increase alpha? When you increase alpha, it shrinks and the ripples, the tails, decreases, the amplitude of the tails. Which is better, to use alpha large or small if you want to reduce intersymbol interference? Large alpha. You reduce intersymbol interference because you have low tails, low amplitude tails. These are confusing if you don't understand them very well. If you want to have less intersymbol interference, you prefer having pulse with large bandwidth or low bandwidth? High bandwidth, large bandwidth. Large bandwidth, because large bandwidth translates to low ripples, low tails. Low tails reduces the intersymbol interference. Think of intersymbol, since we are in time domain designing single carrier waveform, think of it in time domain.
It happens generally at the tail.
Yeah, it happens when there is, it happens when you cross your Nyquist criterion or have mismatch due to channel or synchronization or due to your filter. Your filter was not designed properly. Or any other phenomenon that works like your channel or filter or synchronization. Is it clear when alpha is large, you have large ripples, large tails, high interference, intersymbol interference. When alpha is small, you have low ripples and low interference, and in this case, when alpha is small, you have largest bandwidth occupation. So it's trade-off, you waste your bandwidth. The time response P of t consists of the product of two factors, as I just mentioned before. Sinc, which is responsible for the rect shape, and ensures the crossing of P of t at the desired sampling instant t equal ITB crossing, and another function, another term, which is cosine, which is function of alpha and W, function of the bandwidth and roll-off factor, and this is responsible for reducing the tails of the pulses below the obtained from the ideal Nyquist channel. The decay rate in this pulse 1 over absolute value of t squared. In the Nyquist, in the sinc, was 1 over absolute value of t. So as time increases here, the amplitude decreases faster. The special case with alpha equal 1 is known as the full cosine roll-off characteristics. Under this condition, you have the bandwidth, the system bandwidth, Bt, is equal to W multiplied by 1 plus alpha. Since alpha is 1, 1 plus 1, 2, it becomes 2W. So, summary for what we have just discussed. First, intersymbol interference is a major source of bit error, which degrades the communication system performance just like noise. So we have to build pulses, techniques, methods to avoid it at any cost, because you cannot get your data successfully if you don't avoid it. So to avoid that, we studied Nyquist criterion. We found that to achieve Nyquist criterion, we need to use rect. Rect is impractical. To make it practical, we went to raised cosine, and we understand the price we are paying when we use raised cosine. And we understand what happens when alpha is large, is small, and when you use alpha large, when you use alpha small, whether in time or frequency. All these questions you are expected to be able to answer to. 2. Intersymbol interference occurs due to the dispersive nature of the communication channel. Dispersive, the channel has some delay, like whether it happens in the filter or in the channel or due to any other reason. Intersymbol interference can be eliminated by transmitting the symbols at a rate equals to Nyquist rate. If I tell you what's Nyquist rate, is RB, which is equal to 2W, at least double the bandwidth. This is like sampling rate. Sampling rate has nothing to do with pulses. It was for transmitting your PCM signal. And to reconstruct it successfully, we said the sampling rate should be greater than or equal to FM. And this is in baseband modulation transmission. To avoid intersymbol interference and to get your data back successfully, you need to transmit at a rate, call it bit rate, not sampling rate, which is equal at least to, perfectly, you must be exactly 2W. In an ideal Nyquist channel, a pulse shape filter can be used in the transmitter to reshape the pulses before the bits are transmitted. You must use this, for example, if you want to reshape it using raised cosine, you use this reshape function. Commonly used filters are the raised cosine filters, which are practical filters because you can design them and you can control them by alpha. The raised cosine filter overcomes the practical difficulties associated with the ideal Nyquist channel on the expense of requiring extra bandwidth for transmission. This is the price you pay. If I tell you, you have this advantage, is this advantage coming for free or are you paying any prices here? You pay a price, which is the bandwidth, which is money. So let's understand this by one example. And the example says, find the minimum required bandwidth. What's this? BT, system bandwidth, for the baseband transmission of a 4-level pulse amplitude modulation having a data rate of R equal to 2400 bits per second if the system transmitter characteristics consists of a raised cosine spectrum with 100% excess bandwidth. Without telling you R or alpha equal to 1, R here is equal to alpha. If I don't tell you explicitly, if I tell you 100% excess bandwidth, then obviously this means that alpha is equal to 1. So what do? You just write the formula of the transmission bandwidth. What's the formula of the transmission bandwidth? It's this. BT equal W1 plus alpha. What's alpha in the example? 1. So it becomes BT equal to W. What I need to find? W. Or the bandwidth. So I need to find W. The question giving me the data rate. And it says that we use 4-level pulse amplitude modulation, and this is the bit rate. So what's the simple rate? The simple rate is equal to data rate over number of bits you use for pulse amplitude modulation. How many bits you use? 2. So the simple rate R over K, which is log 2 number of levels. In this case, you have 1,200 symbols per second. The minimum bandwidth is equal, BT is equal to RS, the bandwidth of your signal in baseband is equal to symbol rate RS over 2. This is in baseband. In passband, after you modulate over a carrier, becomes RS. There is no over 2. But here we are talking about baseband, so you put RS over 2. What's RS? We found that RS 1200. You put the value R is 1 over 2, you get the required bandwidth, the required system bandwidth to transmit your signal successfully. Is that clear? Again, you have baseband transmission, and you are modulating this with 4-level pulse amplitude modulation. Now it's giving me the bit rate. The bit rate 2400. If I know the modulation type and bit rate, I can find the symbol rate, because the symbol rate is always below the bit rate, and you just divide by the number of bits represented by each symbol. So how do you find the symbol rate? Divide this number by log 2 number of levels. Log 2 number of levels, how many bits are used to represent each level? 2. Because I have 4. 2 to power how much equal 4? 2. You divide this over 2, you get the symbol rate. The bandwidth, the minimum transmission bandwidth BT is equal to W. How W is related to symbol rate? RS over 2. Don't forget that. I can change the number, but if you understand it, you will be able to generalize it. And then you find the answer to be 1200 Hertz. Now, what the point number 2 of the question. The same for array pulse amplitude modulation sequence is modulated into a carrier wave so that the baseband spectrum is shifted and centered at frequency F0. Now, high carrier modulation. When you go to high carrier, what's the bandwidth? The bandwidth becomes 2, twice it, obviously, before I solve it. But if you want to solve it using this formula, you just remove this 2, this 1 over 2. Remove over 2, you just use RS. But obviously, without using the formula, when you go to high bandwidth, high carrier frequency bandwidth, you know that your bandwidth gets doubled. So bandwidth is equal to W, which is equal to, multiplied by 1200, becomes 2400 Hertz. Example number 2. Suppose a computer puts out binary data at the rate of 56 kilobit per second. The computer output is transmitted using a baseband binary pulse amplitude modulation system that's designed to have a raised cosine spectrum. Determine the transmission bandwidth required for each of the following roll-off factor. So the transmission bandwidth, you go to the rule equal W multiplied by 1 plus alpha. Now W is equal to RS over 2. The question giving me RB, or this is data rate of RB. How to find RS from this? RS is equal to RB over log 2 number of levels I have. How many levels I have? 2, because binary. Binary takes only 2. So you have bit rate over 2. Then you get 28. This is the bandwidth. After that, you substitute it here, 1 plus alpha. Now, for different alphas, the bandwidth, the transmission bandwidth changes. B. For example, when alpha is 0.25, you get 35 kilohertz. As you increase alpha, the transmission bandwidth increases. When you decreases, the transmission bandwidth decreases. So with this, we finish our lecture, and I hope you are clearly understood intersymbol interference and the criterion to avoid it, and raise cosine, and how to solve practical examples on this. Thank you very much for your attention, and meet you in the next part of the lecture.